Have you ever actually stopped to wonder what keeps high-pressure global pipelines from just bursting? I'm talking about those massive networks transporting oil, volatile gases, and critical chemicals across continents, under oceans, and literally right beneath our feet. We always picture the long, straight pipes, right? But the true engineering marvels, the vital joints of this industrial skeleton, are the fittings holding the whole shebang together. Welcome to this explainer. Today we're answering one massive question. What is ASME B16.9? We're decoding the ultimate rulebook for these absolutely crucial joints.
Okay, let's dive into this. Here is our roadmap for today. We'll start with the backbone of piping, define what ASME B16.9 actually is, and contrast it with forged fittings. Then we'll hit materials and manufacturing processes, unpack pressure, testing, and tolerances, and finally, decode the mark of quality.
Section 1. The backbone of piping. Look, the global stakes of moving high-pressure fluids, they just can't be overstated. A failure in a chemical plant or a cross-country gas line isn't just a minor headache. It's a potential environmental disaster. It's a catastrophic safety hazard. So we have to ask, what keeps a high-pressure oil or gas line from bursting at the seams? Well, any piping system is really only as strong as its weakest link. Think about it. When a pipeline has to change direction or reduce its size or cap off entirely, the stress at those junctions absolutely skyrockets. The fittings used at these critical points, they're the unsung heroes of our infrastructure. They are bearing immense internal pressure, wild temperature extremes, and huge mechanical loads.
Moving to Section 2, defining ASME B16.9. To make sure these unsung heroes never fail, the engineering world relies on some seriously strict standardization. Let's shift our focus directly to the standard that actually prevents these catastrophic failures from happening. So, what is ASME B16.9? Simply put, it's the comprehensive standard governing factory-made wrought butt welding fittings. And check out this size range. It's wild. It covers everything from NPS 1/2, which is a tiny half-inch pipe you could hold in the palm of your hand, all the way up to NPS 48. I mean, a 48-inch transmission line is massive. You could literally crawl right through it. This standard covers the overall dimensions, the tolerances, the testing, and the markings for every single one of them, ensuring universal compatibility across the board.
And as you'd expect, these fittings come in some very specific shapes to make up this industrial skeleton. We've got 45 and 90-degree elbows to navigate corners. We have straight and reducing T's to split the flow. There are concentric and eccentric reducers to smoothly step down pipe sizes, caps to just terminate the line, and lap joint stub ends. Each one of these specific geometries is mathematically engineered to dictate the flow of the system, all while safely distributing that intense mechanical stress.
Section 3. Butt-Weld versus forged. To truly grasp what makes B16.9 so unique in the piping world, we kind of need to contrast it with its big sibling, the ASME B16.11 standard for forged fittings.
Now, you might be wondering how they stack up. When you look at them side by side, a pretty crucial distinction pops up. B16.11 forged fittings are generally used for smaller pipes, and they rely on socket or threaded connections. But take a look at the weld type for ASME B16.9. It requires a full penetration butt weld, meaning the fitting is welded edge to edge directly to the pipe. This full penetration weld is an absolute game changer because it allows for critical non-destructive testing like radiography or ultrasonic inspection to verify there are literally zero internal flaws. On top of that, B16.9 fittings offer a full bore that perfectly matches the inside diameter of the pipe. That means no flow restriction and no weird crevices for corrosion to hide out in, which is a big advantage over the reduced bore of those forged fittings.
And that brings us to the magic number in piping design, NPS 2. This 2-inch mark is basically the practical boundary line in the industry. Below NPS 2, designers typically stick with forged B16.11 fittings, mostly because butt welding tiny pipes is, well, it's highly impractical. But the second you go above NPS 2, butt weld standard fittings under B16.9 become the absolute gold standard for both safety and flow efficiency. Moving right along to Section 4, Materials and Manufacturing Processes. Let's peel back the layers and explore the actual DNA of these fittings and how they're physically manufactured to survive extreme industrial conditions. Now, what's really interesting about this is the sheer versatility of the materials permitted under the standard. Depending on what kind of hazardous stuff is flowing through those pipes, engineers can grab standard carbon steel for everyday use, low alloy steels for super high temps in power plants, or highly corrosion-resistant options like duplex stainless steels. The standard even covers exotic nickel alloys, think Inconel or Hastelloy for severe chemical processing, plus titanium and aluminum alloys. ASME B16.9 doesn't just dictate the shape, it literally accommodates pretty much any environment on Earth.
But regardless of the material you choose, they all go through the wrought process. Now, this doesn't mean they're just poured into a cast. Actually, scratch that. It's more like they are highly manipulated. They're formed from existing seamless or welded pipe, tubing, plate, or forgings using tightly controlled hot or cold forming methods. This whole process is specifically designed to change the metal's grain structure, preventing any injurious defects, and ensuring absolutely maximum structural integrity.
All right, Section 5, Pressure, Testing, and Tolerances. This is where the intense math and the rigorous physical validations come in. This is how we guarantee these parts won't fail out in the field. The standard utilizes these incredibly dense, dimensional tolerance charts to ensure total precision. Every single angle, bevel, outside diameter, and center-to-end dimension has a strict plus and minus tolerance, measured down to a tiny fraction of an inch or millimeter. And listen, this precise math isn't just bureaucratic red tape. It is the absolute difference between a securely welded pipeline and a complete, devastating failure. These parts just have to align perfectly for the welder, no exceptions. And buried deep within all those tolerances is a golden engineering rule: 87.5%. Under ASME B16.9, the minimum wall thickness of a fitting must never fall below 87.5% of the nominal thickness of the mating pipe. Even during those intense hot or cold forming processes we talked about a minute ago, where the metal is literally being stretched and bent, manufacturers have to guarantee this minimum thickness just to maintain the pipeline's pressure rating.
Speaking of pressure ratings, this is honestly one of the coolest aspects of B16.9. Engineers use Barlow's formula to calculate the allowable internal pressure based on the pipe's yield strength, diameter, and wall thickness. Because of B16.9, butt-weld fitting is engineered to seamlessly match the connected pipe wall, which is also known as the pipe schedule, the fitting just automatically inherits the pressure rating of that pipe. It's that simple. So if you weld a Schedule 80 fitting to a Schedule 80 pipe, they share the exact same pressure rating. There's no fixed Class 3000 rating like you'd see on those smaller forged fittings.
But of course, engineers don't just blindly trust the math, right? They validate it with a literal trial by fire. When they're qualifying a fitting design, manufacturers have to perform some rigorous proof testing. They weld the fitting to straight pipe sections and just pump it full of pressure until it hits a calculated burst pressure. And here's the kicker. The standard dictates that the fitting must withstand this immense burst pressure for at least 180 seconds. That's a full 3-minute hold with absolutely no failure allowed. This physically proves that the mathematical design works, especially in critical areas like the inner radius of an elbow or the crotch of a T.
Which brings us to our final stop, Section 6, the mark of quality. So how does an inspector out in the field actually know they're holding a genuine, tested, and verified B16.9 fitting? Well, it all comes down to the permanent marking.
Let's move to this and see how it builds a chain of total traceability. Decoding this mandatory mark step by step, you quickly realize it's actually a pretty sophisticated code. Every single fitting has to show 1. The manufacturer's trademark, 2. The exact material grade, like WP5, 3. The wall thickness or schedule, 4. The nominal pipe size, and 5. The heat number. And honestly, that heat number is absolutely crucial. It allows the end user to trace that one specific fitting all the way back to the exact batch of raw steel it was forged from. Talk about ultimate quality control, right?
But hey, you might have noticed something missing from that list, as the standard specifically notes right here. Pipe size, wall thickness, and material identity on the fittings are in lieu of pressure rating markings. This perfectly reinforces what we learned just a few minutes ago. You are never going to see a pressure class like Class 600 stamped on a B16.9 fitting purely because its pressure capacity is already intrinsically tied to its specific size, its material, and that matching pipe wall thickness. So I want to leave you with this thought to chew on. How many ASME B16.9 fittings do you think you walk, drive, or even sleep over every single day without even knowing it? Seriously, from the natural gas keeping your home warm, to the fuel you pump at the gas station, all the way to the complex chemicals used to build the phone in your pocket, it all flows through these unseen joints. The invisible power of this standardization is exactly what keeps our modern, high-pressure world running safely every single minute of the day. Thanks for joining me on this explainer.